Given f of x equals x squared plus 1, find the equation of the reflection in the line y equals x. So remember, if there's a reflection in the line y equals x, that is indirectly asking for the what? Starts with an I. Inverse. And when you hear inverse, what should you immediately say out of your mouth? X and Y switch. So when I ask for the equation of an inverse, what should be your first step? X and Y switch, what you just told me, right? So we're going to get, we always rewrite it. And our first step is always rewrite. Second step is to switch X's and Y's. The very last page of your notes. Okay. So we actually flip almost. Yeah. So, yeah, you're right. So we actually already found the inverse just by doing that. Correct? That is actually the inverse equation. Be sweet if that's where they stop. Sometimes they stop here, and then you guys don't pick it as a multiple choice answer because you guys immediately go to y equals. And you're like, nothing matches. And they literally just swap the x's and y's. I've seen that on the phone, and I'm like, oh, it's too easy. We're gonna keep going. So sometimes this is enough. But more often than that, most equations are in y equals. So I'm going to have to subtract the 1 first. So I get x minus 1 equals y squared. How do I get rid of the squared? And when you physically take the square root to cancel off a squared, plus or minus is what you need. So if on the page they had a square root, y equals square root 7 plus, I gave you one, right? It was a square root. Did you go and put a plus or minus sign in front of it? I hope not, because it was given to you. It was a square root and a square root. You didn't have to get rid of a squared and then square root. That's when you put the plus or minus sign. When you're trying to get rid of a squared and you square root both sides, then you get a plus or minus sign because you're actually physically doing the operation. If I give you a y equals root x plus 3 on the page, done. That's a positive. If it was a negative, it'll have a negative sign in front of it, right? You don't get to just add stuff because you feel like it. Okay, so our equation is y equals plus or minus root x minus 1. Now we want the domain and range of the original and the transformed. Do we need to find the transformed in order to give the domain and range of it from an inverse? No, it's really easy to take the original, the x and y switch. So the domain becomes range and the range becomes domain, right? So let's look at our original. Our original graph is f of x equals x squared plus 1. So that's a parent function, x squared plus 1. The parent function is the x squared, and then I add 1 to it. So I don't need to use my calculator, nor should you have to. You did quadratics in a large degree of content last year. So you should know the parent function of a quadratic. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. You just take your x and square it, right? And you get your parent function. Yes? Of x squared. That's what you should have done last year. But now we're doing what to that parent function? What transformation are you doing to it? Is it with the x? 1 up. My x is like this because the squared's attached to it, right? So that is the parent function moved 1 up. So I can sketch this graph without needing my calculator. I'm going to make my x scale 1. And my y scale 1. All right. So I start at 0, 0, and I need to move 1 up. And 1, 1 is going to be 1, 2. Negative 1, 1 is negative 1, 2. 2, 4 is now going to be 2, 5. Negative 2, 4 is not going to be negative 2, 5. And 3, 9 is going to be 3, 10. Negative 3, 9 is going to be negative 3, 10. So that's my original. We agree? So do we need our calculator if we know what our parent functions look like? No, we should be able to use transformations and move them, right? You should be able to draw an x squared without a calculator. Even just using t tables. 0, 0 squared is 0. 1, 1 squared is 1. 2, 2 squared is 4. 3, 3 squared is 9. Negative 1 squared is 1. Negative 2 squared is 4. Negative 3 squared is 9, right? Just a t table in your head, you should be able to sketch. The parent function, just the x squared. All right. We're going to state the domain and range of the original. What is my domain of that graph? In set notation. Squiggly bracket. We look at our equation. Our equation is y equals f of x. So x is our domain. So squiggly bracket. X such that XER, because it starts at 0 and goes on for life. Out forever. Right? In interval notation, that's negative infinity to infinity. Now, what is my range? Y such that y is what? Greater than or equal to 1. YER. Square bracket 1 to infinity round bracket. Do I need to sketch the inverse of that graph to get the domain and range? No. Could I? How? What's the mapping of inverse? XY becomes YX. So I can take every single one of those points, flip, draw, connect, flip, draw, connect, flip, draw, connect, right? I could sketch it. But I don't have to because of the inverse. My domain is my range, and my range is my domain because my x's and y's switch. So my domain comes from my range. My range is y. Y is greater than or equal to 1, YER. All those y's are going to become what's? X's. X such that x is greater than or equal to 1. X is a nominal real. And interval notation is easy because it's just what it is. Because there are no x's and y's involved. Then my range is easy too if I was my domain, because my range is just my domain with x is becoming y, right? Okay, pencils down for a second, then we'll come back. Okay, so C says, describe how the domain of f of x could be restricted, and we always restrict the domain of the original. It never changes. It's a curriculum outcome. I have to teach you how to restrict the domain of an original function that inverse wouldn't be a function. So remember how we check for functions of a regular graph, like in grade 10? We draw vertical lines through it, correct? And if it passes, which means for every line it only crosses through once, then the original is a function. You learned that in grade 10, because for every x there can only be one y. So if you draw a vertical line that crosses through 2 spots, you have more than one y for x. Okay? Now, how could we test if the inverse would be a function from the original? Horizontal line test. Now let's look at that in a little more depth than we did on Friday, so it makes more sense. Don't draw this, because I'm going to erase a whole bunch of things. I'm just trying to prove a point here. Okay? If I run the horizontal line, 1, 2, 3, 4, at y, is this a y or is this an x? What's it cutting through? Y equal to 5. Did you know that the x-axis is y equals 0? And the y-axis is actually x equals 0? So if I take that, this is on the original. If I take, everyone pay attention to me because I'll lose you. If I take that horizontal line of y equals 5 on the original, that is what line on the inverse? Vertical, because y equals 5 turns to what? X equals 5. And x equals 5 is actually here. And it would be a vertical line once I drew the inverse, correct? So it is just a sneaky way to be able to check if the inverse is a function without having to draw it. On the original, you draw a horizontal line, and that would be a vertical line on the inverse. We agree? Okay. My curriculum to you is that I have to make you restrict the domain, so the x's. So cut that graph somehow in a way that when I draw a horizontal line, it'll pass. Because I want the inverse to be a function. I want to restrict the domain of the original, so when I draw it, the inverse passes. Okay? And we talked about this on Friday. You tell me this. I'm going to undo and redo, so do not do this. If I go from greater, say I restrict the domain to be less than or equal to 1, this part of my graph goes away, correct? Is the inverse a function? No. If I run a horizontal line test on this, it fails at the bottom, correct? So would that be an appropriate domain to restrict this original to make the inverse a function? No. Okay. What if I do this? What if I say, okay, less than or equal to -1? I mean greater than or equal to -1. No. Greater than or equal to -1, does that pass? No. Okay. What happens if I say less than or equal to -1? Would less than or equal to -1 pass? So now I draw horizontal lines across it through once everywhere, correct? Is that the largest domain I could keep? No. Where would the largest domain be that I could keep? The vertex. So I either could keep greater than or equal to 0 or less than or equal to 0. But I could keep greater than or equal to 2, couldn't I? Yeah. That would still pass, wouldn't it? So there's numerous options you can pick, unless I say the largest domain you could keep. Then you would either have to pick greater than or equal to 0 or less than or equal to 0. Both would get you the same amount. Okay? I'm going to pick greater than or equal to 0. So I'm going to restrict, you guys can write this, restricted original domain to be x such that x is greater than or equal to 0, x the noun of the reals. So even though I drew the whole graph, am I going to keep the whole graph? No, because then the inverse is going to be a function. I could keep it if I asked you to draw the whole thing. But if I asked you to restrict the domain like this one, it says describe how the domain of f of x could be restricted so that the inverse of f of x is a function. Sketch the graph of the restricted original and inverse. So now I need to get rid of that left arm, correct? Because I need to sketch the original and the inverse. The restricted original. Well, I kept greater than 0 and equal to, so I have to get rid of all of that. Most people are pretty good with that. Where they go poorly is they don't know how to draw the inverse. Remember, if you have a graph in front of your face, drawing the inverse of that graph is really easy. Whenever you want to move a graph or you want to move points, what should you use? Graph or points, what should you use? Guys, when you want to move a point, what should you use? We went over this 7,977 times, and last week you'd answer this correctly. Mapping. When you want to move a coordinate or a whole bunch of coordinates on a graph, you use mapping, yes? So we would use mapping here. So we're going to go, what's our mapping for an inverse? XY becomes? You want to move a graph, you want to move a coordinate, you use mapping, this whole unit. So my first coordinate is 0, 1. It's going to become 1, 0. Then I have 1, 2. It's going to become 2, 1. Then I have 2, 5. It's going to become 5, 2. Then I have 3, 10. It's going to become 10, 3. What does the inverse reflect on? Yeah.
The graph y equals x.
Yeah. Line y equals x, the identity line. Why does it reflect on that? Because anything on the identity line is invariant. Because anything on the identity line, the x and y's are the same. And if I flip that, it's going to stay the same, correct? Like if I had 1.5 and 1.5 and I flip that, I get 1.5 and 1.5. So I'm going to draw that identity line so that you can see it. So I would draw little ticks through 1, 1, 2, 2, 3, 3, 5, 5, 7, 7, 8, 8, 9. Are there any invariant points? No, because the graph doesn't touch that line, correct? If it did touch the line, every single spot the original touched that line would be invariant, or every single time the inverse touched that line would be invariant. Technically, you're going to touch the line in the same spots, right? Okay, your challenge. This is the hardest one I could give you. Good luck. If you get stuck, that's fine. The first thing you do when you get an inverse of an equation is you think inverse switch x and y's. So we're going to get x equals 3y minus 1, 3y plus 2. Now, why is this harder than the rest of the ones I've given you? There are yep. There's a 2 here. The reason why it's harder is because there are 2 y's, correct? Every other one we've done so far, you just rearrange it to get the 1 y by itself. So you just do like reverse bending. This one, we're going to have to take that denominator and bring it up full thing by multiplication. So I'm going to multiply this by 3y plus 2. And this by 3y plus 2. Then we have to distribute. 3y times x is 3xy. They always list them in alphabetical order. If you wrote 3yx, you're not wrong. A multiple choice answer will be 3xy. Just know that it's multiplication, you can interchange them, right? They just write them in alphabetical order for pretty, I guess. Okay. Then plus 2x equals 2y minus 1. Whenever you have more than one variable, more than one y, you want to get your y's together. Now, we can't combine like terms because one of them is a 2xy and one of them is a 2y, but we do want to move them all to one side. So, I'm going to subtract 2y to move it over with this one. And then I'm going to subtract 2x to move it over here. So I'm sitting with 3xy minus 2y equals negative 1 minus 2x. All right. So I need to get a single y. You see I just moved this one over here, and I moved that one over there. Everything with a y to the left, everything without a y to the right. Yes? The only reason I would ever get everything with a y together is because what do these two terms have in common? I'm ultimately trying to get one y. What do they have in common? What could I GCF out of both of them? What greatest common factor could I take out? A y. Yeah? So let's try it. If I take out a y, out of 3xy, I'm left with 3x. Minus take a y out of 2y, I'm left with a 2. Equals negative 1 minus 2x. How do I get y by itself when it's being multiplied by that factor? So we have y equals, the catch here is the original is in f of x equals, correct? So how do I show the inverse? Well, I can't keep it as a y, and showing it as a y doesn't show inverse. So instead of writing f of x, I write f negative 1x. That shows that that's the inverse of f of x.